Okay. Good morning. Let us start the importance of doping, and you know that in the last discussion I have shown you that the doping basically increases the conductivity of a material. Okay. And we have given you an example that if we add a minute quantity of doping or dopant atom in material, then the conductivity increases by several times, and to get a minimum voltage of say 50 millivolt, we have seen that only required if you get a current of 1 microamp from the sample, whereas if it is an intrinsic sample, then how much voltage was required? Some more than 1000 volt was required. Now, another important aspect of the doping is that if you see this presentation, you will find that gallium phosphide GaP, it is an indirect band gap semiconductor. See, this is an indirect band gap semiconductor whose band gap is 2.26 electron volt. So, if you compare with silicon, this 2.26 electron volt is obviously higher, and it is wide band gap material gallium phosphide. And if you use the relation E equals to h nu and nu equals to c by lambda, you will find that lambda will be 549 nanometer. Okay. That means, the emission from gallium phosphide will be in the wavelength of 549 nanometer, but problem is that it is an indirect band gap semiconductor. So, if it is an indirect band gap semiconductor, so you know that that material is not used for sources, for the fabrication of optical sources, because of the indirect nature of its band gap. So, what to do? Because gallium phosphide can be easily made, it is comparatively cheaper, not cheaper than silicon, but compared to other materials it is cheaper. So, then how to use gallium phosphide for optical source fabrication? And you will be glad to know that almost all light emitting diodes, you have seen the light emitting diodes, okay, in various applications, and almost all light emitting diodes are fabricated out of gallium phosphide. So, if it is an indirect band gap semiconductor, then how it could possible to fabricate a light emitting diode using gallium phosphide? It is because of the doping in gallium phosphide. Not only that, it increases the conductivity of a material, at the same time it gives some valuable property to the material when it enters into the host matrix of the semiconducting material. You see that nitrogen, acts as a donor like isoelectronic trap with a binding energy 8 milli electron volt. Now, there are some new words. One is isoelectronic. You know what is trap? We have discussed trap. Trap basically a defect level. Trap basically a defect level mainly, which can trap electrons inside in the material. And what is isoelectronic? Isoelectronic means phosphorus and nitrogen belongs to the same group of the periodic table. That is why their electronic structure is same, and it is known as the isoelectronic. So, nitrogen when moves inside gallium phosphide, it act like a donor like trap with the binding energy 8 milli electron volt. Now, this meaning of this 8 milli electron volt, you see that this is the conduction band and this is the valence band. For gallium phosphide, it is 2.26 electron volt. Okay? It is 2.26 electron volt, and if you dope gallium phosphide with nitrogen, then nitrogen will act as an isoelectronic trap with a binding energy of 8 milli electron volt. That means, this level it is 8 milli electron volt, very near to the bottom of the conduction band. 8 milli electron volt, you can imagine that if you compare that this gap is 2.26 electron volt, then 8 milli electron volt is very near to the bottom of the conduction band, and since it is the donor level, so it will be nearer to the conduction band edge. Okay. If it was an acceptor level, then yes, it could lie just above the valence band edge or near to the valence band edge. Okay. So, if you put nitrogen in gallium phosphide, then it will give an isoelectronic trap of 8 milli electron volt, and this isoelectronic trap forms a bound electron, a bound exciton. What is an exciton? Yes, it is a pair of electron and hole before recombination. Normally, electrons and holes recombine. Okay? But there are some cases, some electronic environment, some temperature and purity in a material, depending on which electrons and holes do not recombine immediately, rather they form a pair of electron and holes, which is known as the exciton, and that exciton is takes the nitrogen, that exciton takes the nitrogen and they formed a bound exciton. When an exciton is bound to some impurity, here the impurity is nitrogen, which is just 8 milli electron volt below the conduction band edge. So, that nitrogen when bound with the exciton, a bound exciton is formed, and when that bound exciton recombines, finally it will recombine. So, the emission will be there, that means you will get the electromagnetic wave in the form of light. And what should be the value of the emission wavelength? You see that the band gap is 2.26 minus 8 milli electron volt divided by 1.24, and it will be 550 nanometer. Okay. This 550 nanometer is the wavelength of green emission. So, we can conclude that if gallium phosphide is doped with nitrogen in a controlled manner, the emission from gallium phosphide will be in the green region. Okay. And almost all green LEDs which we find in these days are made in this manner, that doping nitrogen in gallium phosphide. Okay. You cannot use the simple gallium phosphide without doping because of indirect nature, but here the trap you introduce. Why this trap is required? It is for the conservation of momentum, we have discussed a little bit earlier. Okay. Now, let us take second example. You see in the presentation, for higher levels of nitrogen doping. Okay. Higher levels means when the concentration of nitrogen is high, increased. When the concentration of nitrogen is increased, then nitrogen molecular complexes are formed in the band gap. Okay. When the nitrogen concentration is greater than or equals to 10 to the power 14, when it is greater than or equals to 10 to the power 14, nitrogen complex will be formed and they will give rise to an energy level in the band gap of gallium phosphide. That means, suppose this is your band diagram, then nitrogen complex where it will be, say here it will be this line, say this green line is due to nitrogen complex, right. This green line will be there, and the emission wavelength will be 590 nanometer. This 590 nanometer corresponds to yellow. Whether it will be green or yellow or red, it will depend on the level inside the band gap. If it is band to band transition, then it will be governed by the value of the band gap. Here the value of the band gap is 2.26. So, without any doping etc., the band to band transition, that means transition from the valence band to the conduction band or from the conduction band to again the valence band, the energy required is 2.26 electron volt, and if you divide 1.24 by 2.26 electron volt, you will get green emission, right. But for yellow you find that 590 nanometer. So, you make a back calculation, 1.24 by 0.59, 1.24 by 0.59, then what should be the energy? Obviously the energy will be less than 2.26 because it is within the band gap. So, it will be less than 2.26. I repeat, if the transition was from say this point to the conduction bandage between these 2 points, the value of lambda will be 1.24 by this gap, and this gap is say 2.26 electron volt. This value will be some 550 or 548-49, around 549 nanometer. Okay. Now, if this is reduced to here, this nitrogen-nitrogen complex give rise to a band here. So, obviously it will be 1.24 by this gap. Okay. So, this gap is say x. So, it is x, that will be 590 nanometer because it will give rise to the yellow band. So, from where you can calculate the value of x, right. So, if you dope something inside the material, it will depend on the thermodynamic and chemical conditions of the material where it will stay inside the band gap, and the transition will be band to band or from band to impurity band etc., right, and that will give rise to some radiation. The mechanism we have discussed, again I repeat that in ideal situation the electrons will be in the valence band. Okay. When you supply some energy, these electrons will move to the conduction bandage or some impurity band if there are some impurities. If there are some impurities, some impurity band will be there. If there are some impurity band, it will go to the impurity band. So, that means here these electrons will move to this green line say. For nitrogen-nitrogen complex, it will move to this green line, not to the conduction band, not required also, right. Then again what will happen? They are excited electrons in that level, they are excited, and what will they do? They will first come to the very fast they will try to come to the ground state. So, they will come back to the valence band where they will recombine with the holes created due to the movement of electron from the valence band to the conduction band or to the impurity level. When an electron moves from this point to say here, one hole is created. So, when this electron again jumps back to the valence band, it will recombine with the holes, and thereby the energy will be released in the form of electromagnetic wave or electromagnetic radiation, and depending on the value you will get different colors of light. Okay. Next example, you see that when doped simultaneously with zinc and oxygen, simultaneously means yes, it at one go, zinc and oxygen are doped inside gallium phosphide. In the first case, we have doped the gallium phosphide with nitrogen, whose value was less than 10 to the power 14 per cc. Then in the second case, for yellow emission, we introduced nitrogen complex, then more and more nitrogen, 10 to the power 14, greater than 10 to the power 14 per centimeter cube. Here not nitrogen, but we use zinc and oxygen. If you simultaneously use zinc and oxygen to dope gallium phosphide, then you will get red emission. The value is 640 nanometer. Okay? You see that from 549 to 550, and then from 550 to 590, and from 590 to 640, basically the energy decreases. The energy decreases. Why? Because the wavelength increases. So, if the wavelength increases, energy must decrease, the energy of the levels inside the band. Okay? Now, what the zinc and oxygen will do? They will occupy the substitutional gallium and phosphorus sites in the lattice. What is substitutional? Suppose there is a crystal structure like this. This is say gallium, arsenic, gallium, arsenic, gallium, arsenic, okay? Then gallium, arsenic, and so on and so forth. If this be the case, a crystal lattice in 2 dimension, then say this is gallium, this is arsenic. So, zinc will substitute gallium. That means there must be a vacancy at the gallium site, and zinc will occupy that vacancy site inside the crystal lattice. Remember that there are 2 positions only in the crystal lattice where the impurity atom can reside, can occupy. One is the substitutional site, another is the interstitial site. Interstitial means between these atoms, yes, between these atoms, these places, between these atoms, these places. Okay? So, either they can be substituted or they can move to interstitial position. I can show you, there is a view graph, and so that the discussion will be simpler. Here you see that in this case the diffusion can be of 2 types. Diffusion means the diffusion of the impurity. Impurity can be diffused inside the material. The doping can be done by either diffusion or by ion implantation. We shall discuss those things in detail. But for diffusion, if you can dope a material by the technique of diffusion, then what they will do, either they will occupy the vacancy position or they will occupy the interstitial position. You see here the one atom is missing, say silicon is missing, or gallium is missing, or arsenic is missing. So, if there is a missing atom, the impurity atom can occupy that position, or it can occupy the interstitial position. But one thing is that for interstitial position, the molecular dimension of the impurity must be small, so that it can occupy the interstitial position, because vacancy site is larger, interstitial site is smaller. Okay? So, suppose there is a silicon atomic crystal, and if you find that there is an interstitial impurity, that means that impurity must have dimension less than silicon. If it is comparable to silicon, then it cannot occupy the interstitial position, it must occupy the vacancy position. So, for doping, either it must go to the interstitial or it must go to the vacancy site. Okay. Now, let us come to our own discussion, original discussion here, that so the zinc will substitute gallium and oxygen will substitute phosphorus. If this is the case, then we shall get red emission. That means, if I draw the diagram, say this is conduction bandage, this is valence bandage, here it is 2.26 electron volt, and say this level corresponds to that zinc oxygen doping. So that the emission wavelength in this region will be red or 640 nanometer. Okay. So, that means we find that the emission from a semiconductor is perfectly depending on the doping. So, not only that the doping gives rise to the enhanced electrical conductivity of a material, at the same time it leads to very good light emitting diode. Let us take another example, say gallium arsenide. Here you see that we are talking about gallium arsenide. Here you see that the band gap is 1.43 electron volt. Okay. And if you use that formula, this formula if you use 1.24 by Eg, you will find that lambda will be 860 nanometer, right. It is basically comes from E equals to h nu, nu equals to c by lambda. C is the velocity of light and h is the Planck's constant, from where you can get 1.24 by Eg, right. And the infrared radiation will come from the gallium arsenide, right. Now, LEDs are made of zinc diffusion into pooled N gallium arsenide or silicon doping of solution grown gallium arsenide. There are two new terms for you, one is pooled, another is solution grown. Basically, we are talking about the crystal growth. When we discuss about the crystal growth, you will find that the bulk crystal is formed by different techniques. One is known as the pool technique. You take gallium arsenide material, very high purity, in a crucible, you heat it, so it will melt, then from the melt you put one seed crystal and then you very slowly pool it. So, if you very slowly pool it, the crystallization will be made and you will get a bulk crystal. So, that is pooling. So, pooled N gallium arsenide means during pooling, when you melt gallium arsenide in a crucible, you add some amount of zinc. You add some amount of zinc or you add some amount of silicon if you grow gallium arsenide from a solution. Various kinds of crystal growth techniques, it can be from solution, it can be from pool, there are epitaxial techniques also, liquid phase epitaxy, molecular beam epitaxy, etc. We shall discuss in this class all those things in detail. So, if you put zinc, then what will happen? Zinc diffuse inside the gallium arsenide crystal lattice and you will find that you will get infrared radiation in 860 nanometer. But problem of zinc diffusion is that zinc gives you band to band transition. That means zinc will be staying very near to the bottom of the conduction band. It is almost, you can say that it is the conduction bandage, the zinc will stay. That means the zinc will give rise to an electronic level which is very near to the bottom of the conduction band. So, if zinc gives rise to the band here, say this is gallium arsenide, it is Ec, it is Ev and it is 1.43, here it is 1.43 electron volt. So, zinc will be very near to the bottom of the conduction band, very near to the bottom of the conduction band. So, the emission will be from almost band to band. Band to band means from conduction band to valence band, band to band transition. And this band to band transition will give rise to an emission of lambda equals to 1.24 by 1.43. Right. If you calculate, you will get around 860 nanometer, which is infrared. But problem of zinc diffusion is that since it is very near to the bottom of the conduction band, there will be reabsorption. You can say, sir, what is reabsorption? Reabsorption means when there will be transition from the conduction band to the valence band, emission will be there, but that emission will be absorbed by the material itself, so that the electrons in the valence band will again be excited to the conduction band. That is the problem of band to band transition in all cases, almost all the cases. Could you get my point? Suppose here the emission wavelength is 860 nanometer. So, that 860 nanometer light, what will happen? It will again be used to excite the electrons in the valence band to the conduction band. What amount of energy is required for excitation of the electrons from the valence band to the conduction band? In this case, band gap 860 nanometer. So, that 860 nanometer light which is coming out from the material from the transition, that light will again be absorbed in the material itself. If it was less than this, so it will not be absorbed. It will not be absorbed because minimum amount is required from is the band gap. It will be either greater than or equals to the band gap for absorption. But in this case, since it is equals to band gap, so the electrons will absorb that light and that electrons will move from valence band to the conduction band, right. So, reabsorption will be there, but reabsorption means from the material the output will be very, very low. If 50%, 60% is reabsorbed, then what should be the output? 40%, 30% will be the output. So, that means zinc in gallium arsenide is not a very good choice. So, silicon is doped in gallium arsenide, and if silicon is doped, the nature of silicon in gallium arsenide is amphoteric in nature. You see, it is amphoteric in nature. It is amphoteric. What is amphoteric? That means silicon inside gallium arsenide can be a donor or an acceptor. Okay. Arsenic in silicon, donor or acceptor? Tell me. Arsenic in silicon, donor. Boron in silicon, acceptor. Nitrogen in gallium phosphide, donor. But silicon in gallium arsenide, it can be donor, it can be acceptor depending on the growth temperature. At which temperature the gallium arsenide is being made, the gallium arsenide is being synthesized, right. Depending on that temperature, it can replace gallium or it can replace, remember that gallium group 3 in the periodic table, gallium group 3 in the periodic table, silicon group 4 in the periodic table. So, if silicon replaces gallium, what will happen? If silicon replaces gallium, what will happen? Yes, extra electron will be there, like arsenic in silicon, you will get free electron. So, in that case, if silicon replaces gallium, it will act as donor. If silicon replaces arsenic, silicon 4, arsenic 5, acceptor, because arsenic has 5 electrons, silicon has 4 electrons. So, in that case it will act as an acceptor. So, depending on the position it is occupying, is it replacing gallium or it is replacing arsenic, it will act as donor or acceptor. That is why it is known as amphoteric in nature. The meaning of the amphoteric is that it can be donor, it can be acceptor. Not only silicon, any material if acts in that manner, that it can act as donor, it can act as acceptor depending on the temperature or other thermodynamic consideration, then it is known as the amphoteric impurity, right. Now, if silicon, if you put silicon here, then the emission wavelength will be 940 nanometer, okay, 940 nanometer, and this 940 nanometer obviously not band to band, because band to band was 860 nanometer. So, it will be inside the band gap, there will be a level due to silicon and it will give rise to 940 nanometer emission. That means, it was say silicon, this line zinc, silicon can be here. So, that the transition will be in the 940 nanometer, and if it is in the 940 nanometer, then it is also infrared, 860 is also infrared, 940 is also infrared, but here there will be no absorption. Why? Because it is less than band gap, it is less than the band gap of the material. Okay. Then there is third example of the importance of doping is gallium arsenide phosphide. It is gallium arsenide phosphide. You see that gallium arsenide phosphide is a ternary material. Why it is ternary? Because gallium, arsenic and phosphorus are involved, because gallium arsenide phosphide is made of 3 elements from the periodic table. One is gallium, another is arsenic and third one is phosphorus. So, since 3 elements are involved, that is why it is known as ternary. Gallium arsenide, it is binary, indium phosphide binary, gallium nitride binary, silicon carbide binary. These are all binary compound. Silicon, germanium, these are all elemental semiconductor. This is known as the elemental semiconductor, silicon, germanium. Then binary, ternary is gallium arsenide phosphide. There are other ternary material as well, like say aluminium, gallium arsenide, Al gas. This is known as Al gas, Al gas. Okay, aluminium, gallium arsenide, this is ternary. Then indium, gallium phosphide, this is ternary. Indium, gallium arsenide, it is ternary. These are all ternary. So, it is also ternary, gallium arsenide phosphide is also ternary, gallium arsenide phosphide. Okay. So, what is this? This P suffix x and AX, AS suffix 1 minus x. What is this? See, this is this one, this gallium arsenide phosphide. You see that 1 minus x suffix is there with arsenic and x is there with phosphorus. What is that? Basically, there are 2 material, one is gallium phosphide, another is gallium arsenide. One is gallium phosphide whose band gap is 2.26 electron volt, another is gallium arsenide whose band gap is 1.43 electron volt. So, that means just by changing the composition of arsenic and phosphorus, you can change the band gap from 1.43 to 2.26. When x equals to 0, what is the material? Gallium arsenide. When x is 1, what is the material? Gallium phosphide. So, that means just by varying x, you can change from gallium phosphide to gallium arsenide or vice versa. That is known as band gap engineering. We can change the band gap of the material by changing the composition. How those things happen, we shall discuss in some later stage in details, but let us take that example of gallium arsenide phosphide, that changing the concentration of phosphorus or arsenic, you can change the band gap of the material. So, if you change the band gap of the material, then emission wavelength from it will be different, because emission exclusively is a property of the band gap, at least the color depends on the band gap, right. So, gallium arsenide phosphide, it becomes direct to indirect for x equals to 0.45. That means, if you take 45% phosphorus, then what should be the value of arsenic? 55%. So, if you change gallium arsenide, if you change x above 0.45, then this material becomes indirect band gap semiconductor. This material becomes indirect band gap semiconductor. Remember, value of x you can change. When x equals to 1, it will be gallium phosphide. When x equals to 0, it will be gallium arsenide. So, value of x you can change, x can be 1, 2, 1.5, 4, x can be 1, 0.9, 0.8, 0.4, 0.2, 0.27, 0.43, any value it can assume, any value it can assume. So, if x is 0.45, then it becomes indirect, that means 0.45, 0.46, 0.47 up to 1 it will be indirect. You see that when x equals to 1, basically it is gallium phosphide. Gallium phosphide is indirect band gap semiconductor, okay. And when x equals to 0, it is gallium arsenide, it is direct band gap semiconductor. So, there is a changeover from indirect to direct or direct to indirect by changing the value of x. Now, if you take x equals to 0.4 in this example, x equals to 0.4, okay. If you take x equals to 0.4, whether it is direct or indirect? Direct, because 0.45 and above it is indirect. So, 0.4 is direct. So, this is a direct band gap semiconductor and it will give red emission. That means, band gap with this composition, that means arsenic 0.6 and phosphorus 0.4. With this composition, it is a direct band gap semiconductor and the value of the emission wavelength is in the red color, okay. The color will be red, that means the value is corresponds to the red emission, the band gap value corresponds to red emission. Now, if you take x equals to 0.65, x equals to 0.65, it is indirect. For indirect, you need some doping. Here, which doping we have used? Nitrogen. Same thing, we have seen that for gallium phosphide we have used what? Nitrogen. So, here the nitrogen we have used and the emission wavelength will be orange. Just by changing the composition and adding some nitrogen, it gives rise to orange. Another example is when x equals to 0.85, 0.85 means it is going nearer to gallium phosphide. What is the value, what is the meaning of 0.85? Phosphorus is 85%, that means it is going towards gallium phosphide. So, arsenic is only 15%. Here also you see that nitrogen is used and the emission wavelength is yellow. So, we can conclude that in ternary compound also, where there is a changeover from direct to indirect band gap or from indirect to direct band gap, there also we can use controlled amount of doping to obtain the light emission from it. So, one thing is the increase in conductivity, another thing is the light emission property. So, those can be achieved by the doping of material inside the semiconductor, and we shall find during our crystal growth discussion that this nitrogen, or we are talking about arsenic in silicon or zinc in gallium arsenide or silicon in gallium arsenide, the quantity is very small. Okay. I shall show you that if you take say 40 kg, 50 kg of silicon, only a few milligram is required for doping. That means, if you take a charge of say 60 kg of silicon, you want to grow a crystal of 60 kg, whose weight will be 60 kg, right. If that be the case, then to dope it with N type or P type, either you will use boron or you will use arsenic, but the quantity of boron or arsenic will be around 5 milligram, 3 milligram. Okay. For 40 kg, I could remember that the boron will be 3.5 milligram for a particular carrier concentration, say 10 to the power 15, 10 to the power 14 type of thing, very minute amount of thing. Okay. So, doping is an unique property in semiconducting material. Yes.
Why we are not using nitrogen as a impurity in case of silicon? It is also pentavalent impurity.
No, it is pentavalent, then oxygen also is there are more electrons, but two things you must keep into mind. One thing is the processing technology, whether the processing technology is available. Second thing is that if you use arsenic or phosphorus, you can, I shall show you that generally liquid dopant is used. Generally liquid dopant is used with very high purity. So, that kind of purity and state of the material you must have. There are several materials, but whether the processing technology is mature enough to use nitrogen is in silicon, that we have to see. Generally the silicon technology is matured with these materials: boron, aluminum, gallium, arsenic, phosphorus, antimony. People have tried with oxygen or nitrogen, but they could not succeed, because you know that that is a chemical nature, it is not a physical type of thing, and there is thermodynamics. Okay. So, within the material there must be some state of affairs where it can accommodate oxygen or nitrogen very cordially, otherwise we will not get the effect. It is like implantation in a body. Suppose your kidney will be implanted, not that you can take kidney from all the sources, ideally you can. Okay. So, there are some considerations using which we use this arsenic, antimony or boron, aluminum, gallium, etc. Right. So, now one thing we can start from today is the doping mechanism. Till now we have discussed the importance of doping, and with related to doping we can say that doping can be done during crystal growth time, during crystal growth. Say, a few amount of the material impurity you can add with silicon or gallium arsenide, etc., that we shall show you. But at the same time you can use two techniques, one is diffusion, another is ion implantation. One is diffusion, another is ion implantation for doping a material. Suppose you want to make a PN junction, suppose you want to make a PN junction. So, you have P type material, you have P type material or you have N type material, then how you will form the junction? You can form the junction by impurity, and that is done by either diffusion or ion implantation. Suppose there is a MOS structure, metal oxide semiconductor, and in those cases you know there is a source, there is a drain, there is a source, there is a drain. So, how the source, drain, etc. are made? Say if the material is p type, then the source and drain will be what type? N type. So, you have to deposit 2 N at 2 corners. Suppose this is the structure. So, here you have to make 2 N type of material deposited, N plus. Plus means heavily doped. When we use this plus as a suffix, say this is N plus, that means it is heavily doped, not lightly doped. So, in 2 areas you have to make use of impurity diffusion, or say that you have a material of P, you want to form a junction N, this is N, to make a PN junction. So, how you will do? You will do using either diffusion or by ion implantation. Now, for diffusion, dopant atoms are placed on or near the surface of the wafer by deposition from the gas phase of the dopant, right. It is placed on or near the surface of the wafer. What is wafer? What is wafer? What is wafer? Thin? No, it is not a layer. Actually, wafer is used as substrate, but what is a wafer? Wafer you have heard during the advertisement of potato chips, wafer thin. You have heard that term, wafer thin. Wafer thin means very very thin. Wafer is a very thin layer. Wafer is a very thin layer, but the material itself can stand so that something can be grown over it. It is a very very thin single crystal layer of a material. Okay, so this is a wafer. This is a wafer. It is very very thin and it has some mechanical strength, so that on which you can grow some semiconducting structure over it. So, when you grow a bulk crystal, generally a bulk crystal is grown where it has a dimension of that type, say 4-inch diameter or 6-inch diameter, a cylindrical type of structure. Okay, say this is some inches with a diameter. Then if you cut into a number of pieces, very thin, how thin it is? 400 micron, 500 micron, 300 micron. So, one piece of wafer means it is around say 400 micron thickness, and the diameter can be 2 inch, 3 inch, 4 inch, 6 inch or even higher. Basically, it will look like a disc, CD, it will look like a CD, but thickness of CD is very very high compared to 300 micron. So, the thickness will be even lesser. So, generally dopant atoms are placed on or near the surface of the wafer by deposition from the gas phase of the dopant. The doping concentration decreases monotonically from the surface. The profile of the dopant distribution is determined mainly by the temperature and diffusion time. What is doping profile? Doping profile means when some impurity is doped on the material, how it will move inside the material. What is the trajectory of its motion inside the material? That is doping profile. So, first you take the wafer, put some impurity on the surface, raise the temperature, it will diffuse inside the material. It will diffuse inside the material, provided you raise the temperature of the wafer. Wafer means the material which you would like to dope. The material which you would like to dope. I shall, in my next class, I shall show you the wafer. So, you take a wafer, put it in a furnace, because from where the temperature will come? Temperature will come from the furnace. Yes, this is, you see, the diagram of the diffusion process. This is known as the open tube diffusion process. Open tube means it is open, both the sides are open, both the sides are open, okay. And you see that the wafers are placed here, and this is electric furnace. That means the temperature of this furnace, of this quartz tube, this is basically made of quartz, the whole thing is made of quartz. Why quartz is used, we shall discuss all those things. So, the silicon wafers are put inside the furnace, and here there is a liquid impurity source. Liquid impurity source, a boron. So, boron has some chemical compound in the form of liquid. It can act as, it is available as solid, it is available as gaseous, it is available as liquid. So, all three states it is available, okay. All three states it is available, and when this nitrogen, the nitrogen is the carrier gas, it carries the impurity vapor to the wafer site. So, say this is a liquid containing boron, then nitrogen vapor will pass through this source, it will carry the vapor to this position where there is the temperature. The temperature can be from 600 to 1000 degree centigrade, very high temperature is required, very high temperature is required. So, if there is a temperature here, so it will diffuse inside the material, and the vent means the other gases, because there will be some chemical reactions obviously. So, for that chemical reaction I shall show you that, say, chlorine will be emitted. So, where the chlorine will go? It will pass out from the vent, it will pass out from the vent. Yeah. Another thing is the ion implantation. Ion implantation is the dopants are implanted into the semiconductor by means of an ion beam, okay, and doping concentration has a peak distribution inside the semiconductor. The profile of the dopant distribution is determined primarily by the ion mass and implanted ion energy. One thing is that, suppose you want to dope arsenic in silicon, so you need a arsenic ion beam. First, arsenic will be converted into an ion beam, that can be done using a cyclotron, okay, that can be done using a cyclotron. And very nearby we have two cyclotrons, one is in Variable Energy Cyclotron Center in Calcutta, VECC, another in Indian Institute of Physics, in Institute of Physics Bhubaneswar, IOP Bhubaneswar. They have a one cyclotron that is meant for material science research, but it is meant for nuclear science research in VECC. Okay. So, the ion mass and implanted ion energy, it will, the profile will depend on these two things. Yes, this is very important curve, and you see that in the first case we have diffusion, in the second case the ion implantation. In the first case it is diffusion, it is ion implantation. What is this? These two are the mask. Mask is like forming a window. That means we do not want to dope in the mask areas, just below the mask we want to dope. We do not want, sorry, we do not want to dope below the mask. We want to dope in the open region where there is no masking. Here you see that due to diffusion, there is a diversion of the profile. The profile has reached below the mask region also. You see, you could not control during the mask region also, and this is basically the lateral diffusion. So, during diffusion there will be lateral diffusion as well, but in case of ion implantation you see that it is almost confined to the window region. Below the mask it has not expanded like the diffusion case. Just if you compare these two pictures, it is confined to this region, but here there is an extended region. So, the profile of the concentration in this axis it is ln C, C is the concentration of the dopant and it is x is the distance from the surface, it is surface, it is x equals to 0 means it is the surface. You see that the concentration is maximum near the surface, the concentration is maximum near the surface, and as it goes inside the material it decreases, monotonically it decreases. Similarly, in this case you see that there is a peak distribution at some x equals to something value. You see that this case that it is dark just below the surface. So, the concentration is very high. Here the dark is at almost at the mid region. Okay. So, in my next classes we shall go into details of this diffusion process, the implantation process, how it is done, what is the energy consideration, okay, and what is the advantage of ion implantation over the diffusion technique, etc. we shall consider. And this is, remember that this type of diffusion or ion implantation is made to form a MOS structure, CMOS structure or a PN junction. Thank you.